Hi, my name is Vadim Selanik and I'm going to tell you about full-duplex radio transmission. So today I will tell you what is full-duplex. I will tell you about full-duplex simulation like time division duplexing, frequency division duplexing, and I will show and explain a working single-channel full-duplex wireless system. So let's start. So, a duplex communication system is a point-to-point system composed of two connected parties or devices that can communicate with one another in both directions. So, in a full duplex system, both parties can communicate with each other simultaneously. An example of a full duplex device is a telephone. The parties at both ends of a call can speak and be heard by the other party simultaneously. The earphone reproduces the speech of the remote party as the microphone transmits the speech of the local party. Because there is a two-way communication channel between them, or more strictly speaking, because there are two communication path channels between them. So, and the opposite is a half duplex. In a half duplex system, there are still two clearly defined paths or channels, and each party can communicate with the other, but not simultaneously. The communication is one direction at a time. An example of a half-duplex device is a walkie-talkie two-way radio that has a push-to-talk button. When the local user wants to speak to the remote person, they push this button, which turns on the transmitter, but turns off the receiver, so they cannot hear the remote person. To listen to the other person, they release the button which turns on the receiver but turns on the transmitter. So there are two main full duplex emulations. There is time division duplexing and frequency division duplexing. Let's start from time division duplexing. Time division duplex refers to duplex communication links where uplink is separated from downlink by the allocation of different time slots in the same frequency band. It is a transmission scheme that allows asymmetric flow for uplink and downlink data transmission. Users are allocated time slots for uplink and downlink transmission. Time division multiplexing separates uplink and downlink signals by matching full duplex communication over a half duplex communication link. So, time division duplexing divides a data stream into frames and assigns different time slots to forward and reverse transmissions, thereby allowing both types of transmissions to share the same transmission medium. So this form of signal multiplexing was developed in telecommunications for telegraphy systems in the late 19th century, but found its most common application in digital telephony in the second half of the 20th century. So the main advantages of the time division duplexing is that the uplink and downlink radio paths are likely to be very similar, and this means that techniques such as beamforming work well with time division duplexing systems. And their other advantage is that the method is highly advantageous in case there is an asymmetry of uplink and downlink data rates. So here you can see a few examples of using this technology. It used in UMTS 3G supplementary air interface TD-CDMA for mobile telecommunications. Also, it used in the Chinese TD-LTE 4G and SCDMA 3G mobile communications air interface. also DCT wireless telephony, and AO 2.16 WiMAX. So the next one is frequency division duplexing. So frequency division duplexing is a technique where the transmitter and receiver operate at different carrier frequencies. For instance, in mobile wireless networks, one block of the electromagnetic spectrum is allocated for uplink, which carries data from mobile phone to base station, as you can see in the picture, and a different and a different block of the spectrum is allocated to downlink, carrying data from a base station to mobile phones. So the main advantage comparing to time division duplexing is that for symmetric traffic such as voice applications in broadband wireless networks, so it's better to use frequency division duplexing. So frequency division duplexing is used most cellular systems, including the UMTS, WCDMA, use frequency division duplexing mode, and the CDMA 2000 system. And also AO 2.16 WiMAX also use frequency division duplexing mode. So here you can see the table with a comparison of these two technologies, and as you can see, in some cases there is better to use frequency division, and in some case time division duplexing, and each has its own advantages. So this is the end about emulations, and now I would like to show you. I would like to describe a working single channel full duplex wireless system. So the main problem in full duplex system, mainly for single channel, is self interference. So it's too strong. Just about 70 dB for AO2 .15.4. So the basic challenge in achieving single-channel full duplex wireless communication is reducing self-interference, and I will show you one of the solutions. It uses cancellation techniques like antenna cancellation, radio frequency cancellation, and digital cancellation. It was introduced in 2010 by all these guys. So this is the general structure of this system. Here you can see two transmitters like TX1, TX2, and one receiver, and other stuff which about what I will tell you a little bit later. So let's start from antenna cancellation. So antenna cancellation involves using two transmit and one receive antennas for wavelengths lambda. The two transmit antennas are placed at distances d and d plus lambda divided by 2 from the receive antenna. So offsetting the two transmitters by half a wavelengths causes their signals to act destructively and cancel one another. So this creates a null position where the receive antenna hears a much weaker signal. You can see on the picture there is one transmitter another transmitter and receiver. So the resize distances between them. So lambda divided by 2 difference in distance gives 180 phase difference between the signals from the two transmit antennas. So you can ask one question like, while antenna cancellation can reduce self-interference from a node's own transmitter, so how this affects the received signal at nodes other than the transmitter. In case of two transmit antennas, the signals from the two antennas get added constructively or destructively at the receiver at distances much larger than the spacing between the transmit antennas. The signals from both antennas undergo almost equal attenuation. With equal received power from both antennas, perfectly destructive combining of the two signals causes the received signal to be zero power. And so as you can see, like on this picture, for equal powers, these areas which are like black color, and in case of unequal transmit powers, the received power at these distances is different from the two transmit antennas. Even when the signals combine perfectly out of phase, the resulting signal is not zero power. So this is a picture for different two transmit antennas with different powers. So this antenna cancellation can give significant reduction at the null position without having a larger effect on reception at other nodes. So their other technique is radio interference cancellation. So radio interference cancellation implements self-interference cancellation in the analog domain using a noise cancellation circuit. The transmit signal is fed to the circuit as a noise reference, which subtracts it from the received signal after adjusting for phase and amplitude. For example, the QH X220 noise canceller chip takes the known self-interference and receives signals as inputs and outputs. The received signal with self-interference subtracted out. The chip allows changing the amplitude and phase of the interference reference signal to match the interference in the received signal. And radio frequency splitter is used to give the transmit signal to the cancellation circuit as the interference reference. So the spectrum snapshots showing the effect of antenna cancellation and a combination of antenna and radio frequency interference cancellation. A combination of the two techniques can give about 50 dB reduction in self-interference. So you can see this three plots: this baseline and with antenna cancellation, and with antenna cancellation plus radio frequency interference cancellation. The next one is digital cancellation. So traditional digital cancellation is used by a receiver to extract the packet from a desired transmitter after the packet has collided with a packet from an unwanted transmitter. To do this, the receiver first decodes the unwanted packet, remodulates it, and then subtracts it from the originally received collided signal. In case of canceling self-interference for full duplex, the transmitted symbols already known, and thus decoding is not necessary in order to reconstruct a clean signal. So the main challenge in subtracting the known signal is in estimating the delay and phase shift between the transmitted and the received signal. So now Using all these techniques like antenna cancellation here, and then radio frequency interference cancellation using this circuit, like for example QHX220. After analog to digital conversion, we use digital interference cancellation, and then we get clean signal, clean information. This technology gives about 70 dB reduction, and it is ready for 802.15.4. So mainly this technology was developed this for this type. So what are the results? So as a first plot, you can see that using a full-duplex scheme, we get like 1.88 median gain in throughput here, and our model is about 8% of ideal full-duplex operation. I mean, like within 8% of ideal full-duplex operation. So, unfortunately, we have little loss in reliability, about 12% on average. So we can see this in this plot. Okay, what are results and main pluses of full-duplex, this full-duplex scheme? So now we don't have hidden terminals. So it's also like we get reduced in round trip time, long delivery and round trip times in multi-hop networks. This great problem, and using the full-duplex, the time is much more shorter because every node can transmit and receive at the same time. So of course we have some limitations. This model is not ideal, and we should have in our mind that there is a few problems, like power limitation. Current prototype can cancel about 70 dB of self-interference, but for AO 2.11, like high power systems, they can have much higher self-interference, and we need more efficient noise and digital cancellation techniques. So for bandwidth limitation, lambda divided by 2 difference from antenna cancellation technique can perfectly cancel one frequency component f corresponding to lambda. So signal components close to f get good cancellation. But current prototype, due to this frequency dependency, is suitable only for narrowband systems such as AO 2.15.4. And working on a frequency independent signal, we should work on frequency independent signal inversion technique to support wideband systems such as AO 2.11. So this prototype not adaptively estimate and compensate for varying channel conditions, and we need channel sounding techniques to estimate varying multipass components to provide adaptive noise cancellation and digital cancellation techniques. What about full-duplex MIMO support? Full-duplex prototype supports single input, single output systems, but it needs to extend antenna cancellation to support multiple streams as in MIMO systems. That guy that introduced this This system, they proposed extension to support me more. So antenna cancellation technique creates a sharp null region close to the lower power transmit antenna, and this is the case of two antennas with different powers. So proposed extension takes advantage of the null region by placing multiple receive antennas in it. So this extension provides a single feedback channel for all the MIMO forward streams, like you can see it here. So this is mainly the end of my presentation. So I took the information in few articles of mainly of these guys, and also Wikipedia. You can find it on the web. So thank you for attention. This is the end.